Our next application of exponential growth would be a very common one for anybody in an algebra class. It's financial models. So the model for the amount of money in an account, assuming no additional deposits or withdrawals, which is a big assumption, makes it kind of unrealistic, but making that assumption, then y of t is equal to y0 e to the kt, and y of t would be equal to the amount in the account. Where y0 is called the principal. That's what it's called in financial circles or an economics class or finance class. It's the initial deposit, right? The principal. T is measured in years, and K is found by using the annual percentage yield. All right, so let's do an example here. So we have an initial deposit of $1,800 is placed in a savings account with an annual percentage yield of 3.2%. Assuming the interest rate remains constant, no additional deposits or withdrawals, again, that would be kind of crazy, but pretend, find an exponential model for the growth of this account. All right, so let's start with A. We know that y0 is equal to 1,800. I mean, that was given to us. And then we know that after 1 year, there would be y of 1, the amount in the account, would be 1,800 times 1.032. Because of the annual percentage yield. But I also know that that should be equal to y0 e to the k times 1. So this is t here, right? This is y0 here, right? So I'm using this model up here. All right, well, I want to solve this for k. I mean, that's what I'm trying to find here because I want to be able to find the exponential model, the exponential growth model. All right, so let's solve this for k. So I'm going to divide both sides by 1,800. And I'll have 1.032 is equal to e to the k, right? Because k times 1 is just k. And then, of course, because we want to solve for k and k is in the exponent, our friend, the natural logarithm of both sides, will help. So I'll have the natural log of 1.032 equals the natural log of e to the k. But the natural log of e to the k, you can bring the k down in front using the power property of logarithms, and it's k times the natural log of e. But the natural log of e is 1. Therefore, k is equal to the natural log of 1.032, which, if I come up with a decimal approximation here, natural log 1.032. It's about 0.0315. All right, so then that means that the answer to part A is that y of t, there are two ways you can write this. You can say it's 1,800 e to the natural log of 1.032 t, or it's 1,800 e to the 0.0315 t. Either one. Now, if you're thinking, hey, e and natural log, they're inverses of each other. Yes, that's because the other way to do this is to not use e at all and say it's 800 times 1.032 to the t. That would also work, but that's not really what they're shooting for in this text. They're really shooting for the e to the kt model. So we're going to write it like that. But technically this is true also, and you can use this to find this. You don't actually have to go to all this rigmarole to do this because you can see how this is always going to work. It's always going to be 1 plus whatever your growth rate was, so in this case 3.2%, so 1.032, and then to put it in exponentials, you just make e to the natural log, exponential of the logarithm, right, to the logarithm of that number. That will always be what k is. All right, so we can make a little note. So the natural log of 1 plus whatever your percentage yield rate is. Little note to ourselves. All right, now for part B. And again, I'm assuming almost all of this you've seen in an algebra class. This is just review before we head into a little bit of calculus regarding this topic. So part B says, how long will it take for this account to reach $4,000? Find by hand. So in other words, you want to set $4,000 equal to your 1800 e to the 0.0315 t. All right, so divide both sides by 1800. And 4,000 divided by 1800 is 20 divided by 9. Again, you could find that with decimals, so don't believe me. Here we go. So 4,000, not 40,000, there you go, divided by 1800, 2.222, and I click that little button over there and it tells me it's 20 divided by 9. Or if you like, you could put 2.2 repeating. That would work also. That is equal to e to the 0.0315. Or if you like, you could say e to the natural log. That works also. But it doesn't really make any difference. It does make a difference if I don't put a 0 in there. There we go. All right, so now, as per usual, we're going to take the natural log of both sides. We're doing that so that we can bring this whole power down in front. So we'll have the natural log of 20 divided by 9 is equal to 0.0315 t. Or if you like, it's the natural log of 1.032. Either way. If you use the natural log of 1.032, because that's equal to, if you use that, it'll be a little bit more accurate than if you use the decimal approximation. But more or less, it's fine. So then t is equal to the natural log of 20 divided by 9 divided by it's divided by the natural log of 1.032. Or if you like, it's the natural log of 20 divided by 9 divided by 0.0315. That's a decimal approximation. Either one should be close enough. So let's go do both of them. Okay, so if I take the natural log of 20 divided by 9, and then I divide that by the natural log of 1.032, I get that answer. If I take it, so it's natural log of 20 divided by 9, and then I just divide it by 0.0315. You can see they're pretty much the same. They start changing around the hundredths decimal place. So this one's 4945 and this one's 5052. But it's close enough. So it's 25.35 years.